Hello, everyone. We are very excited to be here. Everybody, probably as much as we are is anxious, happy. We're kind of sure where things are going, but we are not sure. I'm having a blue light here, blueprints, blue outfit for a good reason. We are very excited to have Jay here today with us. Please send something in the chat if you can hear me, because there's usually a delay. I can hear just now. Okay, perfect. Oh, thank you, Elizabeth. So guys, it's been a very challenging week for all of us, and we are sorry that we added to the uncertainties by delaying the appearance on screen, the same way that we are all anticipating Nevada and the rest of the counts. I would like to take a moment to just thank you for being here. It's wonderful to have community right now. There is a sense of, love and companionship that this community brings to all of our lives. It's a scientific community, but we all kind of know each other by now. And I feel very fortunate that we can all gather together. A gentle reminder, the Learning Salon is a weekly event where we discuss contentions and bridges between biological and artificial learning. I want to invite everyone to feel free to intellectually disagree with each other, but be very respectful of one another. We would like to invite you to ask a question in the Ask a Question area. Remember that you can put your clarification questions in the chat area. And I would love to give a moment to John or Jovo if they want to say something before I introduce Jay.
Actually, no. I'm just extremely honored that Jay is here, and given the week and the difficulties we had, I think everyone's just dying to hear from Jay.
I agree.
Can you guys actually hear me?
Yes, we can. Okay. Very well. The quality is
Good.
Perfect.
Okay, very good.
So we are extremely honored to have Jay here, and probably everyone in the world knows him, but I'm just going to say a couple of things. It's not going to be exhaustive, but I know Jay because he has been one of the giants that the whole field is standing on his shoulders still. And and a lot of the people that I've trained with, a lot of my colleagues, a lot of people that I've worked with have been trained by Jay. So to me, he's a very sort of important root to the huge tree that I'm a member of. So I'm very particularly excited to introduce him. So Jay is a professor at Stanford. And so he was formerly the chair of psychology. You would all know him as one of the authors of the Parallel Distributed Processing, or PDP Bible. That was a book in the 80s, but as we would all know, it's still relevant today. And at Princeton, we still have a PDP. When I was there, I'm no longer there. We still had they still have it. We had a PDP meeting that was in the fashion of the PDP meetings that they had back then in Carnegie Mellon before Jay joined Stanford. So Jay has been a very influential figure. He has won the Mind and Brain Prize, the William W. Cumming Prize, so many things. He's a fellow at the NSF, Rumelhart Prize, etc. There is no exhaustive way of mentioning his contributions to the field, other than he did neural networks before it fell out of fashion. And it is wonderful that within the past sort of decade, it has come back alive, but he kept that field alive and trained people during the time that it was kind of not as fashionable. Among the people that Jay has trained are, John Cohen, Ken Norman, Darsh Kumaran of DeepMind, some of my friends, Anna Shapiro. I think Jess Hamrick might have also trained with him. There's a lot of people that I know who have sort of either directly trained with Jay or they have learned from him. And so I'm very excited to have him here. And Jovo had an anecdote that he wanted to share about Jay. So I'm just going to mute myself, give Jovo the time to do that, and then we hear from Jay.
So Jay and I are on the same DARPA program. It's called Lifelong Learning Machines. And I gave a talk, and I don't know if Jay, you remember this, but it was very meaningful to me. I gave a talk, and Jay asked a question, and it was, I'd say, predictably great question. And then somebody else asked a question, and I said, "Oh yeah, that's just like what that guy just asked," because I had never actually seen Jay before, despite the fact that I spent a summer working in Randy O'Reilly's lab, working on software that Jay had written, and was obviously very well informed about his work. And so that was, I didn't know at the time what I had done, but then afterwards someone came up and said, "Hey, this is, Jay McClelland," to which I was mortified, obviously. And he was just so kind and humble. And it was really inspirational to me to see somebody who was, like I just said, established the whole field, me being an idiot, not even knowing what he looks like. And he was like, "Yeah, you're cool. Like, you gave a great talk. Thanks for answering my question." And it was just so nice and human and so greatly appreciated. So, Jay, I know you have slides. If you click on the share screen button, kind of at the top of your thing, then you should be able to share your slides. And then we're so excited to hear from
Okay. How is this? Can you see?
Perfect.
Can you see my screen? Yeah. Okay. I am. The way things are set up right now, I can't see anything except my screen. So because I had to minimize the other screen to see my own screen, so I know what I'm doing here. So if you need to interrupt me or give me a question, shoot it my way verbally. Okay, so go.
Sure. We will wait for you for 15 to 20 minutes before interrupting you.
All right. If anything major comes up and you really want to break in, feel free. That's fine. All right. So hello, everybody. And I'm honored to be here. And yes, I remember that interaction at the DARPA meeting, and I've been pleased to have a chance to get to know Ida a little bit at NeurIPS. Very fond memories of having a chance to interact with her there recently. So thank you guys for inviting me, and it's a pleasure to be here. My question today is, why are people still smarter than machines? And I just want to begin by saying, hey, I'm a big fan of deep learning. I think deep learning is moving us in very exciting new directions. I feel like these models are building on the principles that we articulated in the PDP volumes that Ida mentioned. And, I'm just having such a wonderful time seeing these exciting developments that are beginning to occur or have been occurring now for 10 years and just keep rolling out and really creating exciting new directions. So we have neural networks that function well enough to be used every day in speech recognition, language translation, and many other things. And they exceed human performance in games like Go and chess. They're getting more and more powerful every day. So in some ways, humans are no longer smarter than machines. But they still are smarter in other ways. And that's what I wanted to talk with you all about today. Essentially, my question is going to be, so what do we have to do to get the brain-inspired learning systems that underlay the PDP sort of ideas and have been burgeoning in deep learning in the last 8 or 10 years to, address these limitations? What is it going to take those next steps? And I'm pretty bullish on the idea that that's going to be possible. But maybe in ways that will be a little surprising to people, I hope, and it'll start a conversation. So what's the problem? Well, neural networks require massive data sets, and they show poor out-of-sample generalization. I think we all know that. To learn to use context in language, we use gradient descent to predict or fill in words using a corpus of 400 billion to a trillion words. To master chess or Go, you use win-lose information derived from self-play for 24 million or 120 million games. Models often generalize really poorly if tested with examples drawn from a different distribution than their training data, while humans are often able to generalize from much more limited experience. So, for example, humans can learn a new reasoning strategy that generalizes nearly perfectly after very narrow experience. So this work is similar, parallel in some ways to the work by Lake et al. That many of you are probably aware of, but it's something that a student of mine, Andrew Nam, has been excited and interested in working on, and makes similar points in some ways. So let's take a look at it. So he's been trying to teach people who haven't been exposed to the game of Sudoku before a specific strategy for solving a subset of Sudoku problems. So humans with no prior Sudoku experience are told that the goal of the game is to start from a grid with some digits filled in and to add digits so that each house, row, column, or 3x3 box has exactly one instance of each digit. So you're looking at a Sudoku here, and there's a highlighted column in this instance. And you can see that there's some digits already in that column. And the question is, which of the two digits that isn't already in that column but is otherwise sprinkled around in the display, can we decide for sure really should go in that green cell in this column? That's the question the subjects are asked to answer. And they're told that you can only put a digit in a cell when you're certain that it has to go there, so it can't go anywhere else. So let's take a look at this case. Let's see, the 2 can't go in any of the blue cells in the same box down there in the bottom middle of this grid. It can't go in the row just above that because there's already a 2 in that row, and it can't go in the remaining empty blue cell near the top because there's also already a 2 in that row. So there's no place else a 2 can go, so there has to be a 2 in the green cell. That's what the subjects have to learn to do, okay? So although most don't get it from just being walked through a description like I just gave you, it's a little bit more formalized and slower. Many participants, about half of the ones who get this far into it, get the idea after a few trials, and after that they make only occasional errors. So this is just showing you over 25 trials, the people who are ending up being solvers at the end of 25 trials are more or less getting it within about 10. Some of them are getting it right away. Others need about 10 to get there. And after that, they're making occasional mistakes still. So they get it in, like say 10-ish trials max, if they're going to get it. And then they generalize nearly perfectly from narrow experience. Well, why do I say narrow? During practice, the target cell and target house are held constant, and only 4 of the digits ever occur as candidates. So here 2 and 9 are occurring. There were 2 others that could occur as candidates during the practice phase. And then during the test phase, we swap the digits that can occur as the candidates. Those are the ones that are occurring 3 times outside of the house. And we also swap the row for column and position within row or column. And we look and see whether people generalize. And in fact, with respect to the digits, they generalize virtually perfectly. That's what I'm showing you in the lower right-hand panel of the graphic there. When we switch the house type from row to column, they boggle a little bit for a few trials, but they're right back on track by the end of, like the first subset of 8 trials, which would be 4 now with the row mixed in with 4 with the column. So, very rapid adaptation, if not perfect, to the house type, and virtually perfect immediate transfer to the digits. And, we can compare this to a neural network. Well, DeepMind had a Sudoku solving neural network based on Adam Santoro's recurrent relational networks. And we can ask, well, does it generalize as well as humans do? And the answer is it does generalize perfectly across all the positional variables, because its ability to do so was built in by the designers of the network. It didn't generalize perfectly across the digits because that ability was not built in. And Andrew and I were actually able to fix that. We could build it in. So we overcame that limitation so that if it learned how to solve with any of the digits, it would generalize automatically to the other digits. So we built in the structure that allowed it to generalize the way humans do. So here's my question. Should we conclude that the human advantage in being able to learn this stuff quickly and to generalize perfectly comes from building systematic generalization in? Well, this is what Fodor and Polishin told us back in 1988. They argued that we can only understand novel sentences or novel ideas because our minds are designed to process language and other sort of structured instructional kinds of streams according to a category and structure sensitive rule system. So for example, for any propositions P and Q, if we know that P and we know that P implies Q, then we can conclude Q. And if X and Y are other propositions, this rule should apply to them as well, regardless of their content. So that's perfect generalization of modus ponens to all propositions, right? According to this approach. And Marcus and Lake and Ullman et al. Have made similar arguments proposing that systematicity is an inherent feature of human cognition and we have to build it in. So I'm going to give you the argument against that. Okay, I'm going to tell you that I don't think that systematicity is a built-in feature of the human cognitive architecture. I think that it's something that we acquire, and those of us with, weird educations have acquired these skills, and we can't imagine that others don't have them. And it's even just those of us who are in the PhD level population who've really acquired these skills in the way that makes us think that they're just the nature of the human mind. Okay, so, well, why would I want to avoid building it in anyway? So the first argument is that, the neural language models that don't build in this structure are far outstripping any models that were ever based on building this stuff in at this point. So that's an argument for why you wouldn't want to build it in anyway. And the other points I'm going to make in the next couple of slides are, well, humans often fail to perform in the systematic ways we'd expect if category and structure sensitivity is built in. And the human ability to perform in these ways is highly educational dependent. The first data point on that is that only half of the participants in our Sudoku experiments actually were able to learn the strategy for MR instruction. And the success rate was much higher for those with college degrees. The rest of the subjects couldn't even kind of get it from the instructions. But here's a couple of other case studies from psychological literature that I've found very, made me think about this and helped convince me that what I'm telling you guys is really pretty much true. So Henry and Lila Gleitman in their work in the late 60s, published around 71, I believe, asked participants to provide a phrase that means the same thing as each of a whole bunch of three-word compounds. Okay, each subject saw 144 of these three-word compounds. And there's two different intonation patterns in which they read. So you could dry birdhouse, okay? You could be asked say what, so a phrase that means the same thing as dry birdhouse, or killhouse bird. What is a killhouse bird? So here are three different responses to killhouse bird. A command to kill a house bird. Taking the life of a house bird. A bird that lives in a place where people are killed. So they asked three different groups of subjects to answer these paraphrasing questions, okay? Some of them were graduate students or persons with PhDs. Some of them were undergraduates or college graduates with no intention of doing graduate work. And the last group were secretaries with high school degrees who had no intention of going to college. And they scored responses in terms of agreement with a system of category and structure sensitive rules. So of those three responses above, only one of them was consistent with this system of category and structure sensitive rules. And I'll leave it to you to sort of think if you can figure out which one. But the subjects were also asked in a different session, which one of these would make sense if it were offered as a paragraph? Which one would you accept? And the data were very comparable. So here's the data. The high school students hardly ever, were much less likely to produce these responses that were consistent with the rules. The undergraduates were somewhat more likely, but only the graduate students were consistently tending to give responses that were consistent with the rules. And so they concluded that this actually, the ability to behave in accordance with structure sensitive rules is associated with an advanced education. That's the point. Okay. What about, that's just natural language, right? But what about systematic reasoning where it really counts, like we're trying to prove a theorem or something like that? There were a couple of educators in Holland in the 50s, married couple, who introduced the idea that there are 5 levels of understanding in mathematics. Really, most people think of it as breaking down into about 3. So the first couple levels were where concepts like a triangle or a square are informal and they're similarity and typicality based. Level 3, concepts involve some appreciation of necessary and sufficient conditions. And levels 4 and 5, concepts are understood as part of a system subject to deduction and proof. So they used this framework to assess high school students and undergraduate math majors' understanding of triangles and quadrilaterals. And their test for level 4 and 5 understanding was this. Suppose you had a quadrilateral with both pairs of opposite sides congruent. Must the opposite sides be parallel? And students had a pencil, paper, straight edge, a compass, and they were asked to explain, they could draw pictures if they wanted, they were take notes, they were asked to explain their thinking as they attempted to answer the question. And most of the high school students just made drawings to try to figure out whether it was empirically true that if you constructed a figure that had both pairs of opposite sides congruent, they would also be parallel. Some of the high school students desired a deductive argument, to use the phrase that they used, but were unable to produce one. They were able to produce one only with persistent probing. So their experimenters like cueing them and giving them all kinds of guidance. Only the undergraduate math majors were able to produce deductive arguments on their own. And I left this off the slide, but the conclusion that both the Van Heelys had originally made and the Berger and Shaughnessy further made was that in high school, almost all the students don't even understand what the discourse is about. They have no idea what it means to prove something. Students would say that, oh, I didn't get the proof part, So the argument was that they were not even talking the same language. They weren't in the same mental space as Fodor and Polishin, for example. Or any mathematician that we might think of. So the interim summary is, Fodor and others may be right that advanced cognitive abilities depend, at least in part, on the ability to reason by means of the application of category and structure-sensitive rules. However, the ability to reason in this way may be an acquired ability rather than an inherent trait of the human mind. And more generally, instead of seeking to overcome the limitations of today's neural networks by building cognitive abilities in, it seems worthwhile to consider how these abilities might be learned. I have no idea how much time I've burned through. I realize it's probably getting to the end of the 20 minutes that I was allotted, but I do want to address this question fairly briefly, and I hope you'll give me a few more minutes to do so.
5 minutes.
Okay, cool. Maybe that'll be enough. So what will it take to build machines that are truly intelligent? Now that we are not going to build in systematicity, if we're going to follow me in this path. Well, to answer that, we need to decide what we think it means to be truly intelligent. And of course, this is a very hard problem. I'm going to give a kind of a non-answer, but it sort of points towards what I think the answer looks like, and we can talk about what it really means. But I'm just going to quote from a couple of people who I think at least were truly brilliant, and see what they thought about it. Poincaré said, "It is by logic that we prove, but by intuition that we discover." And Einstein said, "The intuitive mind is a sacred gift, and the rational mind is a faithful servant." He went on to say, "We created a society that has forgotten the gift and worships the servant." That's not really the point right now. The point right now is that the rational mind of Fodor and Polition and systematic structure-sensitive rules is only a part of what we need. We need this intuitive sense as well, and that's what I think things like GPT-3 and other deep neural networks are, taking us further and further into tapping into. So we need to bring these things together somehow. We need to capture the way these things could work together synergistically. That's what I would say. And so what will it take to build machines that can exploit intuition and acquire systematic cognitive abilities? So I'm going to skip over this slide, but the main point of it is that you probably have all heard from people like, from the author of Blink, whose name is escaping me right now, but that, it takes 10,000 hours to become an expert. But it's not just 10,000 hours of exposure to the corpus. It's deliberate practice. That's what Anders Ericsson had to say. What does deliberate practice mean? It means experts are coaching you. They are providing direct instruction in the most effective techniques and strategies, and they set practice exercises directed at acquiring them. Sometimes and I think usually, in fact, the emerging experts must become their own tutors and guide their own future learning if they're going to eventually really be truly world-class. Expert self-guided practice involves analysis, not just, getting outcome information back from a reward-based RL system. So here's an example, a task we can teach ourselves to perform. This recently started appearing in the New York Times a few months ago now. So here's the deal. You've got this grid, you're looking at it. It's got the only thing you're given by way of information is you're asked to place 2 X's in each row, column, and bounded region in the grid. No 2 X's can be adjacent, not even diagonally. Okay, so I've presented this a 3 times before, and sometimes it's been in a more interactive context. And then I say to the audience, well, some of you, I'm sure, are going to be able to tell me some places where you can already put X's just given this information. And cases where I've done this before, people have stepped up and said, yeah, I see that I could put X's in those bounded regions that just have 3 cells in them already, because there got to be 2 X's in there and they can't be next to each other, so they must be at the 2 ends. So already with just this verbal instruction, many of you, I'm sure, noticed that. And now that I've said that, you can start noticing other things. So you can teach yourself to perform this game. I just want to go through some of the types of instruction and self-instruction that occurs as we learn this kind of game or other games. So we can explain the task itself. That's what I did. I gave you the goal and the relevant constraints, and that's enough for you to get started. So there it is. I can point out, or you can discover general rules that can be exploited. So for example, consider that bounded region with 4 cells in it that's in the leftmost column of this display. Well, there have to be 2 X's in there. So obviously there can't be any other X's in that column. So even though you don't know exactly where the X's go among those 4 cells, you do know that there can't be any X's in any of the other cells in that column. And then what I found myself doing was finding my pencil and sort of putting a little dot in the cells that couldn't have an X. And then, rapidly you can start reconceptualizing the goal, because you realize, oh, I can't directly fill in all these X's, but I can reconceptualize my goal as being the goal of figuring out which cells I can rule out as possibly having an X. So now that's my sub-goal. I'm just going around this board looking for such cells. And it turns out that there are many, many of them. Won't go into the details now, but that allows you to build up additional constraints, which pretty soon cause you to have only, lots of constraints, and boom, you're solving the problem. You can identify a specific sub-goal state that's desirable to reach and explain why it's useful. And I'm not going to go into this very much, but because we're about out of time. But if you play, I was playing backgammon on my cell phone, and I was beating my cell phone, most of the time, but like 60%. I realized that there was something limited about my play. So I bought a book about backgammon, and it taught me to build a prime. So if you know anything about backgammon, sorry, I can't explain it in more detail. The idea of a prime is you create several pairs of your own checkers that are on adjacent points on the board. If you put 6 of them next to each other, your opponent can't get out from behind them. And so if you can create this object with 6 of these pairs of checkers next to each other, then you can, that's a sub-goal. It's not the goal of the game itself, but you can control your opponent's play. And my score just after reading that went up, so I was beating the cell phone like 90% of the time, because nobody ever taught it that strategy. So that's just an example. So what kinds of learning are we doing in these cases? We're learning to make progress towards states that meet desired specifications, rather than learning to produce specific outcomes or to maximize rewards. So this is, in some sense, my main point here. We're doing something really different. We're kind of building representations in our minds of the desired states, with the specifications of desired states, and asking ourselves how to achieve them. In many cases, we can monitor progress by comparing states on the relevant dimensions when we know what they are. Like in the building that prime, it's very easy to sort of ask yourself, how can I make progress towards building that prime? We're often able to articulate the reasons why a particular step or sub-goal is useful for achieving the overall desired specification. This is very different from just training your network with reward signals and or, to imitate expert moves in a game. I know I'm out of time, so I can't go into this in detail, but I think there's another very important thing, which is providing a conceptual framework in which logical and mathematical operations and relations have meaning. So this is a completely unrelated disagreement with Fodor et al., but it's the idea that instead of thinking about systematic reasoning as manipulating symbols according to structure-sensitive rules, you have to think about it as providing a notation system within which you can notate meaningful relationships between quantities. And this is an alternative formulation that's well understood in the mathematics education literature. So I would argue that intuition may be the appreciation of a previously undiscovered relationship, within the underlying conceptual framework, though it may ultimately be described in the notation of a symbolic expression and proven by symbol manipulation. So that's what Poincaré and Einstein were talking about. They're appreciating previously undiscovered relationships within an underlying conceptual framework, and the symbols and the logic are just there to like verify that all of it. There's no gaps in the proof. So we're skipping this bit, but we could come back if you had questions or a topic I'm very interested in. So share an email with me. So next steps towards neural networks with human-like cognitive abilities. Most deep learning models rely on mapping inputs to outputs, predicting future inputs from past inputs, or learning to maximize reward. We need to add to this by teaching neural networks to engage in discourse as people do, including teaching them to follow instructions to carry out specific tasks, adopt specific goals and or sub-goals, conform to specified constraints on allowable actions, make targeted corrections to their behavior, understand and provide explanations, connect language and symbolic expressions to an underlying conceptual framework, and reason within the framework rather than simply manipulating symbols. My lab and others are beginning to explore these kinds of issues, and I think this will lead us closer to human-like machines. There's one last further step we need to take, and it's my final slide. Ultimately, intelligent agents discover their own explanations and build their own conceptual systems. At the cutting edge of science, we are basically setting our own goals and devising self-explanations that we can then express in language and other constructions and share with others. Creating neural network-based learning systems that can do these things will be an exciting future challenge. And that's what I had to share with you today.
Thank you so much, Jay. This was awesome. So we are, many people are currently clapping in front of their monitors. I feel like maybe I should turn on another light. I'm beginning to look like a character from a movie with the blue halo. This was amazing. So typically, Jay, after these after your amazing talk, typically the three of us ask a couple of things or discuss with you a couple of issues, and then we open the floor and then bring people on the screen. There's already 12 questions, and people have been voting on those questions. There's been a lively chat going on in the chat section. We've had Melanie Mitchell, Paul Smolensky, and a number of others there, and so we're excited about a sort of a lively discussion today. So I wanted to maybe first, John, do you want to go first? Jovo, should I start? Does anybody want
to? I'm happy to ask questions. A little intimidated and happy. Okay, so thank you for that. It's not the second time I've seen some of that stuff. I've watched some of your talks online in preparation, and so it's always great to hear your perspective on these things. My question for you is really about the first slide, which is the question, which is something like, why are people still smarter than machines? And so I mentioned something about this on Twitter, which is that people typically say that we are smarter than machines. But of course, in certain ways, machines are much smarter than us. For example, they're much faster doing matrix multiplication than we are. They can also memorize, say, white noise or pink noise patterns more quickly than we can. And I'm sure there's lots of other ways that machines are smarter than us. Similarly, dogs are smarter than us in certain ways. Right? Dogs can learn patterns of smells more effectively than us. And that's a really complicated computational problem because there's this plume and there's all sorts of chaotic dynamics. And so I guess my question is, in what sense do you mean that we are smarter? Clearly, in certain ways we're smarter, and in certain ways we're dumber. So what does smarter than mean to you?
I always thought that Dave Rumelhart and Jeff Hinton were smarter than me because they were thinking about things that I hadn't realized I should be thinking about yet. And they were formulating new ways of thinking about them that nobody else had thought of, or only a very like Jan McClelland sort of thought about it at the same time Jeff did, or Dave and Jeff were thinking about it, but only a very few people were really sort of like realizing that we have to move in this direction and find a way of adjusting the strengths of connections in deep multi-layer neural networks in order to make them be truly relevant to understanding intelligence. And Einstein led us to new ways of thinking about the universe because he realized that there were some unresolved puzzles and some interesting contradictions that required him to think about them in different ways. And Darwin discovered natural selection because he knew that the other ideas that everybody was propounding just didn't make any sense to him. And he spent 20 years of his life trying to figure out an alternative that would make sense. And it took him a very long time, but he finally came up to it with it. And so it was because he was able to orient himself towards a particular goal. He set a goal for himself of finding an explanation of evolution in terms of something that made mechanistic sense to him. Like the inheritance of acquired traits did not make mechanistic sense to him. And so he wasn't having that. So, okay, so what could make sense, right? So what it means to be truly intelligent is what my last slide was about. It's being the person who sees the world in a new way, reconceptualizes it, and shares it with others so that we can benefit from their insights.
So,
John, do you want to go next? Should I go? Or Jova, do you want to?
I think that's a really interesting answer that I totally didn't expect. It sounds like you've defined human intelligence, which is a great thing to try to characterize. And it's not obvious to me that that's what intelligence writ large is, or general intelligence is. And maybe you're saying that human intelligence is that.
Okay. I don't want to quibble about the definition of intelligence. I think that probably we shouldn't. So I accept your point in that respect. I think that, I just think that it's a feature of an intelligent system that it can do these things in addition to things that deep learning systems are already doing. And extracting statistics from experience is something they do better than we do. In part because they can be given more of it, at least text experience, in part for all kinds of other reasons. So I don't want to get involved in quibbling about what intelligence means. I just would say that a dimension of intelligence is this kind of thing that I'm stressing so far our deep learning system.
So, Jova, are you? I want to ask a very quick one. So I grew up learning that systematicity and compositionality are properties of languages, or properties of learning a language in general. And so pretty much everyone, whether they can even write or not, they have as long as they can speak a language and understand the language, it seems to me like they should have some level of systematicity. And I read your wonderful new sort of perspective paper, and I really appreciated it. And I also sensed there, especially towards the end paragraphs, that you are sort of laxing this requirement of language a little bit. So I'd love to hear your thoughts on that, whether you think systematicity, you're saying that it needs education, but is it already in language? Do people already display it in language? And do you see a difference between these two notions of systematicity? And second, whether your current view of language, as I read in that sort of neuron perspective, do you think you have lacked the idea that language requires systematicity?
So I have been arguing for, since Mark Seidenberg and I started to talk about this, I would say we have been arguing But I think it was also, maybe it wasn't stated explicitly, but it was definitely part of the thinking in the past tense work with Rumelhart. Okay, and the idea is this: it's certainly a part of Joan Bybee's thinking, and her articles were very influential in getting Dave to start thinking about those problems as well. So this is the this idea that I've been trying to get everyone to appreciate, but I haven't fully succeeded. I've written several articles, like with Joan and with other people, sort of trying to promote this viewpoint. So let me see if I can capture the essence of it. Languages are actually not fully systematic. The reason why voters' notion of building structure in has not worked in computational linguistics is that it actually doesn't fully characterize the nature of the way languages actually work. They are not fully systematic. In Bybee's way of thinking about this, there's a lot of competition because we want to be efficient in communicating specialized meanings which aren't fully compositional, and so we hijack things that would be compositional and they get used for these somewhat non-compositional meanings, and then they stop having compositional phonology, and there's a vicious maybe virtuous cycle whereby this stuff all occurs, such that languages develop, exceptions arise in language. Why does that occur? It's not like we're just forgetting about the rules. It's in the infrequent things. It's actually the most frequent things that become exceptional. Why? Because we use them so often. It's costly to unpack the compositional formulation, so we compress them. And so if you're stuck with a system whereby you're going to reason with structure sensitive, categorical, like if it's a verb, it takes ed, you're just not going to capture the actual nature of actual language as it exists. So I believe that language is, I use the phrase quasi-systematic, quasi-regular. It's not fully regular. And that's why it hasn't worked to use that standard approach. So that's what it was that was specifically called out in the Google Neural Machine Translation paper in 2016 as the reason why it was working better than explicit manipulation was because they had many, many layers of gradually adjusted parameters that were able to learn how to take into account the nuances of the way each language expresses certain ideas so as to be able to capture those aspects that cannot be captured by those rules. So that's the first part of my argument, my comment, my answer to your question.
So let me
the second part. Wait,
yeah, go on,
wait. There's the second part because you asked about the article. There's the second part, which some people may see as going against the grain of this, but it's another question of like, well, why would languages be systematic in the somewhat systematic, like quasi-systematic, right? Why would there be as much systematicity as there is? And here's my argument about that. And this is, you could call me a generative semanticist if you'd like. I know that movement died, and nobody calls themselves that anymore. But the idea is that language ultimately reflects the structure of the things that we talk about. We talk about objects, and each one of us human beings on this event is a separate, discrete object. Any one of us could drop out without affecting anyone else's participation. That is a compositional fact about this event. John can reach up and pick an apple from a tree and give it to Mary without, changing the whole future of the universe. Now, actually, there are matters of degree there, right? So the other apples on the branch, one of them might fall because the branch got shook. And maybe Mary had a boyfriend and he's jealous when John gave her the apple. But, most of the world wasn't affected, right? So there is this tendency for individual actions and events to have very sort of systematic and local kinds of influences. And that's why language tends to be that way as much as it is, but it's never perfect. It's always partial and proximate, and therefore it's not going to help to force it into the Progressian bed of making it so, which is what Chomsky and others may have thought was a good idea at the time, but I don't think is.
So, if I may, I'd like to separate two things. So, just like you, I'm not on the sort of Chomskyan, Fodorian, Pinkerian train. I much would sort of prefer a learning approach to all of these things. So I'm not on the innate sort of group. I definitely identify more with the sort of learning approaches. However, I think there is a distinction to be made about systematicity in terms of the approach, the Fodorian suggestion of building in things, versus systematicity as this idea that if you acquire any language, as you're acquiring that language around the age of 1 or 2, you're also acquiring the systematicity as a human, for instance, right? And so in language, you can display the behaviors when you're using language that display systematicity. Now, they might have gotten it wrong. I wonder whether you think human language or humans, when using language, do display systematicity to some extent.
To some extent, their behavior can be partially characterized as though it were systematic. That's the way I like to put it. Yes, it's extremely useful to say that the past tense of most words in English is formed by adding ed and making a slight phonological adjustment depending on whether the word already ends in a D or T or not, or whether it's voiced or unvoiced. And that's, a sufficient description of 97% of the tokens of verbs in the English language. It doesn't happen to be a sufficient description of 50% of the actual, types. It's not a very good description of the types though, because the high frequency types are all exceptions. So it's just like, we're not behaving, and the whole point of that Gleitman study that I mentioned was that those of us who've been inculcated in formal education, including diagramming sentences in the 4th grade, which I don't know about you, but I had to do that a lot, and there's a lot of, it's not exactly correct syntax, but there was syntax. It's something that is already being taught to us, right? Our thought processes are being structured in such a way to convince us that it really is such and such a way when it's, only partially so. Now, I did want to respond to something that I saw coming through in the chat, which I totally agree with, and which is a main thrust of the article that you mentioned. So just I agree, and please see that article for more on this. But it's the idea that it's not the language that is giving us the systematic structure. It's the world, okay? It's the fact that when you pick up an apple and you eat it, the other things that are sitting there don't get affected, right? That your actions on the world have highly compositional consequences. They're not perfectly compositional, as I already tried to indicate, but they are largely so, and language is compositional in response to this aspect of the world. Okay, so it's not from language that and this is the thing that drove Chomsky really insane, right? The idea that it wasn't all coming from language, but I just think he's deeply wrong about that. I don't think that it's coming from language. I think it's coming from the world. The world is actually quasi-compositional.
I fully agree with you, in fact. And There are a lot of wonderful questions and wonderful sort of guests. So I'm going to give time to John and then have people on screen. I just want to say that in Iran, we play backgammon a lot since we are young and with everybody in the family. So if the world opens and we see each other in person, I will bring a backgammon board to a conference and ask you to play with me.
All right, we'll see who wins.
I haven't played in a long time. So John, do you want to?
Yeah, so thank you very much. I really enjoyed all the points you're making. It's stuff that we've talked about here in the Salon before, and I find myself agreeing with you as the talk went on, right? So in other words, when you got to the end and you basically produced this list of things we're going to have to add to supervised learning and reinforcement learning, I can do nothing but agree, right? And you talked about concepts and all sorts of extra things that we've discussed a great deal. So I don't want to go there because I kind of agree. And of course, I couldn't tell how we're going to do it. I mean, you said you're starting to work on it, but as far as I can tell, it's just a giant gap that you're admirably addressing and bringing attention to, but it's a gap. And I'm not convinced that we know how to formalize or even go after that. But the whole argument you made about people of different levels of education having to learn things, yeah, I mean, you practice and you do things better. You have bad chess players, good chess players, and extraordinary chess players. But there has to be some core competences to begin with to put practice on top. I mean, we only have to talk about the numerous studies that have been done on language acquisition in non-human primates to show that all the learning you can do, they don't manage to develop, and I'm not going to anywhere near the system activity. So in other words, if it was just learning, we should have fluent chimpanzees with us right now, and we don't. Okay, so in other words, we could send them to college. They've lived, as you know, probably better than I, they've had chimpanzees live with humans in the house while little babies are, they've done it. They've actually done it.
Yeah,
They
Seidenberg
never
had something to do with
acquire.
those studies too.
So in other words, right, they never acquire all these easy systematic. So in other words, I'm not even convinced that, you know, whether you learn very quickly between 0 and 1 or whether you have it, to me, I don't really think it matters that much. Once you concertina it into such a short time frame, something very special is going on. You get a core set of abilities, whether it's modular, whatever it is. And then, of course, practice. You know, I was lucky enough to have, you know, Anders Ericsson came to the Santa Fe Institute, and we were able to talk with him at length about practice. And there were a number of interesting things. One was, of course, that if you want to get good at chess, you at least need to understand the rules to begin with. Right? You need to understand, somebody has to instruct you what the rules are, you have to understand the concepts, and then you start to practice, okay? The other interesting thing about practice, which is really fascinating, is that you undergo a qualitative change in representation. In other words, that you begin to do things quite differently as you practice tasks compared to the way you began them, right? Hence these studies showing a correlation between IQ and how you acquire chess as a beginner, but no correlation between IQ and chess master status, right? Very interesting things like that, right? And it's controversial. So in other words, why is it so important to you to, it seems to me that you need to get rid of anything innate, anything that you have to begin with, because you seem to think that that way, at some point with learning algorithms, we'll get the whole shebang. So that seems to me what this is really about is, we may not be there yet. Supervised learning isn't going to cut it. Reinforcement learning is going to cut it, but some kind of learning will. Hence your slide that said what kind of learning is going on here. But I don't think you need to get rid of all innateness in order to feel like you've got a nice blank slate. We just have to work out the learning algorithm and we'll get everything, right? That just seems to be your argument. And after that, which I disagree with, all your laundry list of things we still need, I completely agree with.
Okay.
I just don't see why you have to be so strong-headed about either or.
Okay, thank you. This is a beautiful question, and I really appreciate it, and I'm very, very pleased to be able to try to respond. I think I have three potentially unrelated thoughts about it, but I know I have at least two. So let's see if when I get through two of them, whether there's still a third. The first one is that while I agree that humans and chimpanzees are light years apart in terms of what they can do, there are multiple different perspectives on why that is. And there is this one sort of, there's just this one special thing, and that it was this language thing that happened. It's a parody, of course, of anybody's position, but that's a way that people frame this, and they're looking for understanding what that one special thing is. There's another perspective. Barbara Finley is the main protagonist of this, to my knowledge, and I am kind of a disciple of hers in the same way I'm a disciple of Joan Bybee's when it comes to language. That there are actually, like, the everything's different except for the lower level sort of primitive systems. There's been a burgeoning, an explosive expansion of huge territories that are very, very minimally developed in primates, in chimpanzees even, okay? Chimpanzees have a lot more of it than macaques, and macaques have a lot more of it than rats do, but it's still a huge difference, and there's many, many facets to it. There's visual spatial facets, there's things having to do with auditory processing, there's things having to do with multimodal integration and layers upon layers that didn't even exist. It's like, so there are definitely architectural difference between humans and non-human animals, no question. But what are they? I don't know, but they do exist, and I have to acknowledge that. So it's not one great big undifferentiated mass of connectoplasm, as somebody once said, characterizing my views back in the 80s. I've been, perhaps naively propounding this overly emergentistic framework for all these years, as Paul Smolenski well knows. So let me come to that. Why would I kind of like push this angle, right? And it probably doesn't matter except insofar as it causes me to look for explanations that are not the ones that, Fodor or Lake and Tenenbaum seem to be tending to want to look for. And I just believe that we ought to have people like me taking this position and pursuing it for all that they can towards finding these other factors rather than the individual differences factors that you were, the species difference factors. So I'm not saying that those are not relevant as well and that we should think about them, but we shouldn't look for just one element that's the magic key. It's going to be a huge diversity of differences in brains between chimps and humans. And we should consider what I'm advocating as a research strategy, not as a statement of belief. Okay, so I perhaps I go too far towards taking it as a statement of belief. But that's where we have common ground anyway, right? That's the part of what you agree with all these things. We should be doing all these things. So that's all I'm really advocating, is that we do them. Now, here's the third point, and I do want to acknowledge this. And the article that Ida mentioned, by the way, in the PNAS goes into this, and I think it's important. It's certainly very important in my own thinking, and basically, there is an architectural innovation that distinguishes the models since the introduction of transformers, query-based attention, as I call it in this article. And that's so different from what was happening in LSTMs. And there's been lots and lots of interesting articles written about that. So there's an article that was brought to my attention by one of our co-authors in which the author says, see, linguists had it right all along. you had to have access to all the detail of all of the past stuff in order to properly decide how to kind of inflect the next bit or interpret the next bit of the input. You couldn't pass it through a limited channel bottleneck. That was what he thought linguists were saying all along, and I thought that was interesting because I hadn't read it that way. But there is a big difference there, right? The LSTM is passing everything through a narrow bottleneck. It's very limiting. In the attention-based approaches, you can query anything in the window that you have. And the article then goes on to, well, what would be some of the limitations on what those windows might be like, and how do we make it so that they seem as fluid and plastic as possible so that we can potentially exploit more context than we know how to exploit so far. Okay, and that's, to me, that's another, huge thing about what makes people and neural networks smart. GPT-3 is, why is GPT-3 smart? That's what GPT-3 is doing. It's querying this huge extent of prior temporal context using query-based attention instead of passing it all through, a single LSTM or even multiple LSTMs, right? So it is an architectural innovation. But the last time I had this conversation, I wanted to make sure that it was clear that this architectural innovation is not specifically tied to language. It's actually equally relevant for all other aspects of our behavior and engagement with the environment. So as to be able to behave in appropriately context-sensitive ways, we need to have all kinds of prior context in the similar way that we do in language. And so it's not like it's specific to language. It's not a language-specific feature. It's an architectural innovation that has transformed neural networks since 2015, and it's going to continue to play out as we're seeing in extending the use of this architecture into all kinds of other domains besides language. It happens to have been most strongly first exploited in language. So I agree that there are architectural features that are important, but I tend to err on the side, just this is my bias and inclination, of looking for the ones that are going to be truly general, right? That are going to be exploitable in all domains instead of like just thinking, oh, it's an encapsulated domain-specific kind of innovation. Okay, those were my 3 points.
Well, thank you. Just one quick follow-up on that. I just don't want it to make it look as though that I was in any way trying to propose sort of a language-centric view.
Oh, okay, yeah, you probably won't.
Point did I, and just as you know, there's been some lovely work showing all sorts of dissociations, between cognition. I mean, an aphasic patient, a globally aphasic patient, can play chess. Right? You can, there are many cognitively dissociable disorders. Wonderful work. I'm trying to remember the name. She's new faculty at MIT, I think. Nemiroff has done beautiful work showing preserved cognition of many types in people who've lost language. When you look at the difference between non-human primates and primates, there are many other abilities they don't have, which are not related to language, like imitation, certain types of tool use, and things like that. So in other words, it's not sort of an obsession with language is the main difference.
I didn't mean to paint you that way. I was in case that was what you were thinking.
Right. No, I mean, I think there are many other ways that one can think about intelligence. Okay, well, look, there are tons of very, luminaries and others in the chat dying to get in and have their go at you. So I think I should... But it was fun talking with you, and we'll...
Oh, wow. I haven't been so stimulated intellectually in a long time, so yeah.
Oh, wow, thank you. Okay, so let me just... Ida, there's so many people, I don't know how to do this.
So we're going to have Melanie as our first...
Hi, Melanie.
In 1 second. You probably know her.
I don't know, Melanie, if you and I have met, but yes, of course I know who Melanie is.
Okay, so Melanie, we don't have the video or your voice. We just have your icon. Oh, there she is. Hi.
And I invited Paul too. I just thought it'd be cool to have all three of them on screen at the same time.
Okay.
Hi.
Paul.
Hi.
Hello.
Yes,
Can you hear
please
me?
go ahead. Yes, please go ahead.
Thank you so much for this great talk and fascinating discussion. So here's I have a kind of a two-part question. First, Jeff Hinton recently, or has often asserted
Have I been
that,
hearing something? Because I don't hear anything.
oh,
I was hearing before, but not now.
Paul, can you hear me?
No, he can't hear you, so he's interrupting you because he can't hear that you're already
Yeah,
asking your
okay.
question. but why don't you, Paul?
He just muted himself, so I think we're good.
Okay, great.
So Jeff Hinton has asserted that deep learning is going to be able to do everything. And that's actually a quote, which is, I just want to point out, is different from the statement that learning is going to be able to do everything, which is what we were talking about before. And my first question is, do you agree with Hinton that deep learning in some form or another is going to be able to do everything? And then here's my second question. So it's related. In your last slide, you talked about next steps for neural networks with human-like cognitive abilities, like build their own conceptual systems, understand and provide explanations, connect language and symbols to concepts, and so on. And it seems like this is incredibly ambitious, and maybe even like almost equals all of intelligence. And why are you optimistic that neural networks can learn to do all this?
So I'm not sure that I intended to say that, I'm so optimistic, at least in the short term. I have no, I would not endorse Jeff's statement if you asked me, because I don't like to predict the future. I don't actually think I know what the future will bring. And so I will just profess a somewhat greater degree of agnosticism about what outcomes are going to look like. As I was saying in relation to the previous questions, it's a research strategy for me to pursue these kinds of alternatives. And I tend to have a certain degree of belief that they'll turn out to be productive, obviously, or I wouldn't think it was a wise thing to try, but I don't know for sure. And, I would say over the years that, 30% of my projects have just fallen flat and they'd had to be abandoned because no progress occurred. Whether we're ready for progress along the lines of some of the things that I was asking about, I'm really unsure. I think there's something interesting about the question of whether, deep learning or something is going to solve the whole problem. I mean, you can come at that from many, many different angles. So for example, if we really think that we should never rely on systems that aren't very, very deep in the literal sense of many, many layered deep, we may be misleading ourselves. That may not be we may need complementarity with more shallow systems, for example. And I think we do exploit that in the brain. So, and whether what it is that would cause you to say that this is part of deep learning, but that isn't, and so you'd be able to get a well-defined sort of answer to that question when you saw it, is another question, right? I don't think, what does Jeff mean when he says deep learning? Does he mean that it's all got to be based on gradient descent from explicit error signals? Well, no, he doesn't believe that. I know that because he's very interested in unsupervised learning, right? So what does Jeff actually mean when he says that? And we would have to ask him. I think that it's worth trying to understand more about how the brain is solving these problems. And I've often spent some of my time and effort thinking about that, or thinking about the constraints that facts about the way brain damage breaks cognition down into semi-separable components. I think we should be continuing to think about that as sources of clues, and whether that falls under the heading of deep learning, I just don't know. I think it's true that most of the breakthroughs that we've had in the last few years have come more from the computational side than the biological side. And I think that's an interesting fact. I don't think it's an inevitable fact, and I don't think it's necessarily true of the future, but I think it's true of the recent past. And I also felt like I was one of the last people who thought I should join the bandwagon of thinking I shouldn't sort of constrain my thought a bit more by what seemed biologically plausible to me than I was noticing others. So Jeff and Dave were running off and being, doing things that Francis Crick was absolutely disapproving of, because the brain couldn't possibly be doing those kinds of things. And I was sort of like a little bit on the fence myself about those things back in the day. But I joined the bandwagon because it helped me understand cognition a lot better to adopt the computational approach rather than trying to wait to adopt it before I knew how the brain would do it. So in that sense, it's been a productive bias to look for the solution in deep learning like things. And maybe that's all Jeff really means by that when he says it. I don't know if I answered all parts of your question.
No, that's really interesting. Can I just do a quick follow-up? So one of the items on your wish list for neural networks was to understand and provide explanations, which I found really interesting. What is it? What would it be for a neural network to understand an explanation?
It would be for the neural network to be able to use it to find a strategy for solving a problem or deriving an insight without, from just the explanation rather than a bunch of demonstrations of examples. Yeah, I feel like maybe I should work up an example of this that's clearer. But I think it feels to me as though it has a lot to do with what we used to call means ends analysis, right? It has to understand to understand why you want to build this prime in backgammon it's useful to understand why. And when you read about it, the explanations are telling you why it's useful, right? And there's several good reasons which you sort of understand, and that helps you appreciate what you're doing when you're building it, and to know whether what you did counted as a solution that was consistent with the reasons why it's a good idea in the first place. And this is a difference between, understanding why you're going on an errand and going on the errand and carrying out the literal instruction that, so Little Black Sambo is based on this kind of idea, right? That you could literally follow the instruction and think you were doing the right thing, but you wouldn't have understood what truly was meant by it. And that led you to do something that was literally valid, or seemed literally valid, but wasn't actually underlying valid. So that's what it means. And it's hard to adjudicate in practice. People try to assess it in exams. But being able to engage in productive thinking and some of the kinds of things that I think that people who criticize neural networks have held up as challenges are among the things that we want to be addressing. It's not like I'm claiming that we shouldn't be trying to address those things. It's that we shouldn't be trying to address them by building in certain things. I don't know if that was
Great.
that's
Thank you.
okay. Thank you. Thanks. Interesting.
Paul, you've been waiting patiently down there in the right-hand corner. Can you hear us? You're muted.
Ida, do you want to introduce Paul? Because he's never
You're muted,
been on the
Paul. There's a
Salon
mute
before.
sign.
So, Paul, if you scroll on your image and then go to the top left, it's not working? Then Jovo can sort of drop you and then invite you again. This has happened to me before. Sometimes when I change the modality of output, it does happen. So, okay, let's try this. So for everyone else, this is Paul Smolensky. You would know him as the person who tries always to bridge together sort of connectionist and neural network approaches with symbolic approaches. And the word tensor would appear very much in a lot of the work that he does. I particularly enjoyed a multiple part speech or lecture that he gave at Microsoft Research, because he's also a member of Microsoft Research, other than being a faculty at Johns Hopkins. He gave a little about the history of cognitive science and neural networks, in fact, and he did mention sort of the Fodor versus the sort of the Chomsky Fodor innate people versus the McClelland. He called it East Pole versus the West Coast sort of disagreements. So I'm excited to see what Paul is going to ask. And Melanie says Paul wrote one of the most influential papers in neural network on the proper treatment of connectionism, indeed. And a very spicy paper in BBS. Thank you, Jonathan. What's happening?
I don't see Paul Smolensky. I don't see his name on the thing unless he's some user number thingy.
I can find out.
Can you type in your name?
He sees no invitation, he says.
He says, okay.
Yeah.
His name is user 8995407F. I'm gonna put it here. Yeah, everybody else is saying it too. Yeah.
Thanks, everybody. Sorry.
There he is again.
Hi, Paul. We're happy to have you.
Well, thanks. Sorry for the technical difficulties. I guess I look at the issue of compositionality this way, that wherever you look in cognition, you see compositionality. Our conceptual structures are compositional. Our plans are compositional. Our motor plans and our high-level plans, both. It's everywhere. And it may be that you want to say there's quasi-compositionality everywhere, and I'm perfectly happy to say that. The thing is, I don't think our networks, our models, are quasi-compositional everywhere the way that our minds are. So something is missing. And it's true that compositionality is inherent in the world. Then maybe it's like the fact that three-dimensionality is inherent in the world, and maybe our evolution has given us some sort of knowledge of this, or at least priors to construct mental structures in a quasi-compositional way, let's say. The symbolic apparatus, when it's usually deployed as discrete symbol processing, I think is fatally limited by the discreteness. I do believe in continuous structure, continuous compositional structure, and that we should bias our deep learning systems so that they are driven to construct these kinds of representations. That should be an inductive bias that's profoundly important in the learning process, if they're going to learn the way that we learn, or at least if they're going to arrive at knowledge systems like we have. So my thought, what I'm pursuing at the moment, is we can break down the sort of, we could call them primitives, that's maybe not the best word, of symbolic computation, the things that give it the power to build compositional representations and exploit that compositionality. We can break them down into little pieces such that if the pieces are arranged the right way, a neural network can behave compositionally and look, in fact, almost like a discrete symbolic system, but crucially, it's not discrete. If we can break things down and then impart our deep learning models with those primitives, so that deep learning can learn to construct compositional structures of its own, invent its own kind of compositionality, because it's been given the primitive raw materials to do so. And those materials give it an inductive bias that pushes it to do that. Then maybe we would take a big step forward in increasing the compositional generalization ability of deep models, for example. So that's how I'm thinking about it. And I don't think that it necessarily is in contradiction to what you're saying, but it does invoke this possibility that we have inductive biases in the form of apparatus for building and manipulating compositional structures, albeit continuous, not discrete ones. So I will stop here.
So,
Thank you.
Paul, I just one quick question before you. So, is that compositionality going to have to be hand coded in? In other words, I think the question that Melanie asked was, when Geoffrey Hinton says it's all going to be deep learning, and then the thrust, you know, with Jay was it's going to be learning, but where are all these primitives going to come from? Are we going to provide them and then deep learning starts to munch on them, or aren't you just letting go? So aren't you letting GoFi in the back door? Aren't you basically letting GoFi in the back door?
No, I'm letting it in the basement. I'm putting it in at the bottom, the very foundations of GoFi, so that a system can learn to build a much better compositional knowledge system than GoFi could build, and one that's inherently non-discrete.
So a bit of both, basically.
Yeah,
Yeah, I'm just thinking that we want to give deep learning the materials to work with, and then let it do its magic.
So if I can respond to you, Paul, you know, I guess the idea that it comes in the basement versus that it comes as a result of acculturation and education is the difference that I would like to emphasize. I don't want anybody to think that I'm going to convince them to do it my way versus your way by what I say right now, but I would like to just point to the examples that I was trying to go over. No, it went by pretty quickly. That's the nature of the beast, but where the things that people have wanted to build in aren't present in the ordinary adults who aren't inculcated in the culture of formal thought. And maybe that didn't come across clearly enough. So let me be a little bit clearer about this.
It came across, but I think it misses the point.
Let me finish, okay?
Mhm.
Okay, well, okay, you may think that, but I'm gonna make sure it came across for a couple of other people as well. So the ability to appreciate a deductive argument and realize that it establishes conclusively that certain things follow from given premises is something that Fodor was taking for granted and that I think was a mistake. And there may be certain kinds of primitives that aren't those things, but they don't involve number either, right? Because that's another example where many people were saying, okay, well, integers, those are the innate parts of number, and you know, everything else maybe is a bit more learning based, but all cultures have integers and therefore it must be innate, and then Peter Gordon goes to the Amazon and finds a culture where they don't. And he finds out that they don't actually appreciate some very, very basic properties of exact equivalence, for example. So I think that the concepts that we reason with and that give us the power that we have as educated scientists is something that we take hugely for granted, and that my ability to think according to structure sensitive rules is something that is a product of my acculturation, and it's a powerful and important consequence of that, which is what allowed, like Newton, to do everything that he did, building from his insights, and Einstein and even Rumelhart figuring out backprop. He needed the math as well as the intuition, and it was the synergy of the two that really led to the real intelligence there. So I don't know. I'm not exactly sure what kinds of primitives you ultimately are building in. But I do appreciate that there are pressures that must be operating on representations that we have that tends to make them to be more systematic versus more kind of idiosyncratic, right? And this is a theme of the distinction between dense representations and sparse random conjunctive codes that has been part of my thinking for a very, very long time. If you want to memorize something specific, you assign a single neuron to it, or a very sparse distributed representation that minimizes its overlap with anything else. If you want to sort of make it be part of a broader system, you pass it through a narrower bottleneck. And I think that narrower bottleneck may be a part of encouraging this quasi-systematicity that, maybe we both agree that that's what it's going to look like. One of the things that I guess I wouldn't want to think it's going to look like is any commitment to any particular notational system or something like that, right? So it's like if it's a pressure to pass things through a limited capacity bottleneck that promotes generalization, that's one thing, but it doesn't constrain it to particular content in the same way as it's got to be consistent with X bar theory, for example. Right? So X bar theory is a particular theory of content of syntactic structures, whereas this is a very, very much more general sort of constraint on the representations that we use when we think, and much more inclined towards that general constraint that may encourage the kind of thing that you're looking for. And if that's what you're building in the basement, I'm fine with that.
I'm just trying to go after what a 4-year-old can do, not what Newton can do, not what Fodor can do. I'm actually not putting any weight on the kind of arguments that say that we can follow modus ponens. That has nothing to do with the importance of compositionality as I see it. I think that the people in the Amazon can construct a compositional plan on how to get to the next valley without any problem. Okay, they don't need to be educated to do that. Okay. And so I just think that there's a huge amount of compositionality in a 4-year-old's knowledge system, and we're miles away from that in deep learning. So that the whole layer that you're talking about is way higher than I'm shooting for right now. And I agree that the arguments about how universal and innate those abilities are is very questionable. But that's not where I put the burden of proof that compositionality is important in cognition. I mean,
okay. So what we need,
sort of, I just raised this, which is that anyone who speaks a language masters a very rich compositional system, quasi-compositional, but compositional, and they don't need to go to school to do that. They may need to go to school to diagram sentences, but who cares about that? We care about the fact that they can master this incredible system.
So I would like to just tell you why I started thinking about Erickson and his ideas.
Mm-hmm.
It was because I heard a talk by Eve Clark,
Mm-hmm.
who is a developmental psycholinguist. And Eve and Annette Karmeloff-Smith falls into the same camp in a certain kind of way. And I just want to share this thought with you guys. Eve, well, actually, Eve's perspective is rather different from Annette's. And so I'll just make it about Eve, and we can come back to Annette if anybody's interested. But Eve's perspective is that children are getting a huge amount of the kind of thing that Erickson was talking about. Explanation-based descriptions of why you say things this way and not that way. And, much more in the way of structuring of their learning of language than certainly way, it's not just you get, loads and loads of exposure to text the way that real text like GPT-3 does, but you get targeted corrections that, no, you should have said that this way. It's usually not, no, you should have said it this way, but it's like, oh, did you mean this? Did you mean to say that? And the kid then picks that up and starts saying it that way. And there's also this meta conversation about this stuff. Maybe a little bit less in the 2 and 3 year olds than there is a little bit older, but it's the notion that there's no discussion about like nouns and verbs or synecdoche categories, even among 4 year olds, is wrong, and 4 year olds are profoundly enculturated already, I would say. So I just, I don't want to be seen as totally rejecting the idea that we want to build in a bit more. Many of you have been urging that, and I don't want to sort of make myself sound like I'm like totally rejecting any of that. I just want to emphasize that there's not enough attention that most people are paying to the way in which the environment enculturates and starts to contribute to the development of a metacognitive kind of framework, even at the level of 3 and 4 year olds.
Thanks for that answer and those questions. And we have a bunch of guests who are in the UK. We want to make sure we get them on before they go to sleep. So thank you, Melanie. Thank you, Paul. And I'm going to invite a couple of other people on now.
Thank you, Melanie and Paul. I think
Zena.
I think Zena had a question from Paul. Maybe we want to keep Paul. Okay, so Paul is gone too. So we have Jane and maybe Ferial wants, she said that she has sound issues, so she didn't want to sort of be online, but she said that Jane could perhaps ask her a question as well. So
we're having Jane on and then Zena. Is that
hi, Jane.
How are we doing?
There's Jane.
Great.
Yeah. Also, if you invite Zena while Jane is talking, that would be awesome.
Jane, do you want to introduce yourself to everybody?
Yeah, I'm a research scientist at DeepMind. I had the pleasure of meeting Jay when he was visiting us this past year. Yeah, I work on meta learning and still dabble in a bit of neuroscience. So really great talk, Jay. I guess me and Ferial's questions kind of were basically along the same lines, and I think also Paul touched on aspects of this in his question as well. But we were just wondering, or at least to me, it seems like a lot of. Oh, I just lost video.
I can see you. Oh.
She's gonna reconnect. I think something happened. Usually it's just a connection thing. We lost Zenat. So Did you do this, Jovo? As you disappeared, the two of them got kicked out too.
I think this is a Jedi move. Only you could have done that.
We lost both of our. How did you manage that? Okay, if you invite them again.
It's so nice having you.
Josh, what did you do?
I really don't think I can take credit for that. I'll take credit for certain things.
Can you invite them back?
They're both accepting and connecting.
I think the elections is breaking the internet right now. Everybody's having internet issues.
So it has been the last couple of days. Jane is not available to be invited. Then is.
Okay, invite Zena because I guess maybe oh god.
Oh, Jane's back.
I should just ask how much longer we're going to go, because there was an event that starts at 3:15 where I'm a expected faculty participant.
I guess
And it's 3:06 right now.
as long as you're willing, we'd be
Okay, so 9 more minutes-ish.
great.
Okay.
Sorry, my laptop just died.
Okay, we have you back. Go ahead, Jen.
Sorry. Yeah, so I think we're basically wondering if language is something that, it seems like a lot of what you're saying builds upon the need for language, or the need to basically classify the world, at least somewhat symbolically, and then communicate it to somebody else. And if that's something that needs to be built in, and also and how would you build in this aspect of language and needing to sort of communicate it either through like a bottleneck or some kind of something like that?
Yeah, I think there's actually something kind of interesting about that idea. So when, you know, and this is something I think about a lot, just as I introspect about my own cognition, which is that I feel like I sometimes know what I'm going to say before I say it, but other times I don't really know what I'm going to say until I hear myself say it, right? And I remember when I was a first-year graduate student, I used to think, I want to be part of this conversation, and I know I'm going to have something to say, so I'm going to stick up my hand, and then when I get called on, I'll find out what it is, right? And there's something about that process of actually articulating your ideas that turns out to be profoundly important. And so yeah, I think there's something about what you said that resonates with all of that. That movie, in which the aliens communicated by sending out, you know, blobs of sort of, I don't know, ink-like stuff that would spread into sort of circular patterns and stuff.
Arrival.
Right, was a kind of, maybe there would be different kinds of constraints that would come from that, but maybe they ultimately would be ultimately the same. So the fact that we have to push the information through a limited capacity serial channel is presumably causing some of the constraints that cause languages to be the way they are. We exploit parallelism in language to a certain extent, like, you know, so we have intonation patterns that can ride on top of the phonology, for example. But to a large extent, we are restricted to this sort of sequential modality, and that must be an important part of the constraints there, and that's worth keeping in mind. So to that extent, I think I'm in agreement with you. The other thing is that you tapped into the idea that, well, maybe the underlying thing is that we want to communicate with each other. And I guess I would have to agree that maybe natural selection had something to do with that. You know, that rather than gaining our relative advantage through entirely internalized individual discovery, we have this incredible leverage of being able to share an understanding of the world by saying things to each other. And that, that's kind of, it comes back to all the things that I was talking about at the end of the talk, where, and the way I think about it is language provides us with a huge amount of information about the world that we don't have access to otherwise. For example, the fact that something belongs to somebody else, or that they may have put poison in that glass, or, you're looking at two glasses, you're about to drink one, but somebody tells you, oh, somebody dropped some drops of something, it might be poison in one of those glasses. You only got that through language, right? This is important information about the world. And humans learned to develop a system whereby they would leverage their ability to share this information with each other. And that's gotta have been tremendously important in, the emergence of human cultures and societies. And then, okay, so, but is it fundamentally more about the building a system that's good for sharing representations of situations and events than it is about it being a language itself? That would be the direction I would take further thought about that. I don't know if that connects with the question, but that's where the question took me.
Yeah. I think it does. And I've also heard that part of what allowed us to even get consciousness is that we developed internal dialogue, which allows us to sort of pass observations and thoughts through that bottleneck of language. And that through the process of talking to ourselves, that's sort of what allows us to develop systematicity, or like the ability to abstract and form higher level thought and maybe even consciousness. I don't know if you had any thoughts about that.
I find it, I get my most self-critical and wooden-headed whenever I find myself talking about consciousness. I don't know how to do it effectively. I admire Dan Dennett for his ability to do it, but I feel like I'm not very helpful when we go there. But the idea that language forces us to categorize does resonate a bit with me, and if I say to you, oh, that person is, a woman, or that person is a man, I am, or that I don't know, I'm communicating a huge amount of information to you. And if you use it like, well, typically, blah, 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 then you would derive certain implications from that, which might or might not be true. And I think we have a tendency to overuse categorization to sort of straitjacket and overinterpret, the characteristics of others because we've labeled them in those kinds of ways. It works perfectly when it comes to algebra, because if I tell you if something's a real number, then, all kinds of things that apply to all real numbers suddenly apply, and that's beautiful. But if I tell you somebody is an African-American, as we've been learning in the latest election, it tells you much less than we thought about what they're likely to think about their preferences among the presidential candidates, for example. And this is something. So this categorization aspect that language brings does sort of push us in this direction of over systematizing, and in some domains it turns out to be extremely powerful, and in other domains it's profoundly misleading, and just where we should be in how to sort of navigate that space adequately and sort of get the right implications when appropriate and not otherwise is, I think, one of the things that's extremely difficult. So that's part of what I was trying to, the kinds of, I think I should stop there.
Jenna, Jane,
Hi.
Do you have time for one more question? It's a very interesting one.
Yeah, let's take this.
Yeah.
This will be the last one for me today. And thank you for
Sure.
just. Let me say, if I don't get a chance, it's been wonderful to see people like Paul, meet Melanie, and meet some new people that I didn't know. So this is great, and thank you all for doing this. Yeah. So,
well, last but not
go ahead,
least,
my man.
Zen. Yeah.
Cool. So yeah, thanks for the great talk. I guess I've got two questions, and they're tied and related, and it's both to yourself and also to Paul, who's left. So if you look at what Paul talked about, kind of notion of compositionality or continuous compositionality. So the question I have there is, what does this mean precisely? I have an intuition, but it seems like in both that case, we know kind of from symbolic systems that we know how to build discrete compositional systems. And so I wonder, at the core of that is the notion of recursion. So recursion is one of the key concepts which underlies compositionality. And I wonder if we extend that to this kind of continuous world, does that same core notion of recursion extend to the continuous compositionality? But more related to your work, again, going to this notion of the example that you showed at the end, where you had the grid world, and you inferred that you had to have a piece in one of the ends of this kind of this three cell box. Again, we have an understanding of how to kind of prove or understand that that is true, but there's a sense as a human, I have an intuition by which it's true. So what the question, which I'm not saying very clearly, but the question that I'm getting to is, for many of these different systems, we understand kind of an idealized version of how to reason with it. And I wonder, when we extend that to kind of the messy real world, how many of those principles transfer over, and how many of those principles have to be innate versus learned from experience?
Well, I think those are, I don't have answers to all those questions myself. I think about things like that a lot. And I guess so many people have argued that insight is a fuzzy sort of partial activation kind of thing with several little clues sort of all conspire together to make something pop into your mind, and you have like, oh, here's an insight. Thing about that is it might or might not be the right answer. It might be a free association, because it may be that those fuzzier sort of activation based kinds of processes are not constrained to conform themselves to the reasoning principles in just the right ways. And this notion of how the early stages of understanding are more similarity based, and as people educate themselves in mathematics, they become better able to exert control of thinking in terms of the formal relationships and things like that. I think there's a reality to that, and I think, but it's often believed that if you overextend that, you will block the access to the insight, and you'll just be doing symbol manipulation, right? So there's a tension there that I think is part of the question that I was asking us all to think about. What, how do we preserve the intuition while also getting the systematicity? I think that's a great question. It's kind of the question I'm also trying to answer. And I guess I think, but both Poincaré and Einstein were sort of onto something, right? And philosophers at Stanford have made similar arguments before, that mathematicians have these insights, and the proof process and the process of writing it down is something that fits in with a formal scheme, is something that's a whole nother process that's unrelated to that, or not not necessarily completely unrelated to that, but may obscure all of the factors that led to the insight in the first place. So I do think that to an extent, what I'm looking for is how we sort of harness the approximate quasi tendencies that neural networks, I think, inherently tend to have, which gives them their leverage in dealing with natural language, to get to places where we can actually do valid and explicit reasoning in ways that are truth preserving, as opposed to sort of activation conservation or something like that. So it's a great question. I'm not sure how much that got at it, but it's definitely something that I think about a lot, and maybe you'll have some interesting developments yourself in thinking about these kinds of things. All right, so thanks a lot, everybody. I'm going to take off now.
Thanks.
And yeah, it was fun.
Thank you very much.
Try to join in
Pleasure
again
having you.
another time.
Yeah.
Take care.
Cheerio.
Zena, stay where you are. Adam, hello.
Okay.
There will be life after Jay.
I know we can't.
Okay.
No.
Your voice got very quiet.
My voice got quiet?
Yeah.
Really? Okay.
Yeah.
I don't know why. I'm the same person.
Adam, do you want to ask your question? Well,
Yeah.
Go
I guess
Adam.
I'm gonna go. Maybe John can answer it, or Ida. So I was surprised that the entire
answer it too, or Zena, you know.
the entire conversation seemed to be, and actually you asked this question already. It was about exceptional intelligence in the beginning, about what Einstein is good at, and sort of really unique people. And then it became about language. But it seems to me that animals are really, really good at a number of things that machines are still not good at, that don't require language. But it's been hard to define exactly what that is. So what would be the sort of the right way to frame this question? What are formally the problems where we have this sense that animals are really good at learning things? And there's, of course, lifelong learning aspect of it. That's one thing. But maybe there's others.
Adam, can you give a concrete example, just because you know this literature so well, of something that animals do really well that machine learning and AI still fails to do?
I have a tough time giving you a concrete example. So I think what they're really good at is that they are able to they're robust, they survive, right? They never, never really have to reboot them. You never have to kind of redo something, right? They just figure out how to survive in a world, and sort of many of these animals are very flexible. There's a sense that they learn about their surroundings. And yeah, I mean, the specific examples I would give are too specific. I think animals have, and frankly, I'm most thinking of mammals. But perhaps that's already too specific. Maybe non-mammals have this too. Capacities of interacting with the environment, learning about it in ways that machines just don't do yet, and that clearly don't require language, although they might require some of the same compositionality being represented in different ways.
I mean, again, Adam, I know we've discussed this. I mean, I think that whenever you talk about intelligence, you have to decide whether the intelligence should be defined in terms of the performance or the flexible acquisition of new skills as the world presents them, right? I tend to prefer that definition, right? When it comes to all the animals that you talk about, they're given a repertoire by evolution. And then when animals are flexible across habitats, what happens is you get evolution because of their high reproduction rates. So rats that, manage to do certain things in New York City outbreed the ones that don't. But definition of flexible out, new skills, right? It's hard in the animal kingdom because they have so much of a repertoire that is selected for, which they can then parameterize, right? And so in other words, I think you're having a hard time because it's difficult to show, and there are examples, right, in birds and in non-human primates, but intelligence can be baked in by evolution. It's incredibly intelligent what animals do. A spider weaving a web, a bird making a nest, a beaver making a dam. That's intelligent behavior, but the credit goes to evolution, not to the animal, right? And I think that what's really interesting is that there are, what Jay was talking about with all this duplication of prefrontal cortex is you can start to sort of simulate evolution in the lifetime of one animal. That's intelligent, right? So in other words, I like Francois Chollet's definition, which is it's not experience, it's not evolution, it's not inductive priors, it's flexible acquisition of a brand new, surprising skill.
But again, you're starting from the human definition.
No, it's not a human one. I'm saying that intelligence, there's a lot of intelligence at the level of performance, right? Now, if you want that to be your definition, then a spider's intelligent, a beaver's intelligent, they're all intelligent because they're doing clever things in the structure of the world. The question is where does the credit go?
My question was narrower than that. Clearly, humans are smarter than animals in the way in which you define it. So not to generalize that a spider is really smart. It is. But machines, all the different algorithms, even if we just go away from deep networks and reinforcement learning, seem to be limited in some ways. That animals are not. It feels like they're kind of like a closed system where the different algorithms that are in them make them work well. You can say that it's all just well designed to be flexible and they're unable to learn. You can take that position. But if you believe that they learn something, I think it's obvious that they're able to learn something new. They manage to do that in a robust way. They survive.
I want to hear what Ida has to say about this, because she made some faces.
Can you hear me?
Barely.
Oh, I don't know what's going on with my voice.
Oh, no, when you held the mic up, it was okay.
Can you hear me now?
Yes.
Okay, perfect. So a couple of things I want to say to that. First of all, we are doing this project where we are not defining any rewards, and we are having basically we're having reinforcement learning agents that are homeostatic, so they have to move around to figure out when to move towards somewhere to increase calorie, when to sleep to not be tired, etc. So gradually reward develops like that. So I agree with you that there is a way in which not being driven by explicit rewards, but being driven by some kind of a homeostasis in order to figure things out and passing sort of generation to generation the kinds of architectures that might make this easier. That's a very important feature of in my opinion, biological intelligence that is subhuman. And I'm totally with you that we need that kind of ground up intelligence, and reinforcement learning at Microsoft Research, we are doing a couple of things in that direction. The thing I wanted to say in terms of the distinction you drew between machines versus animals, I am with you in that I'm not a very big fan of the complex Roomba approach to AI, which is AI is built, some neural network is built for a particular task, very specific task. This can be chess, this can be Go, but it's basically a Roomba in the sense that it has a purpose and it was built for that purpose. It's not that it can flexibly learn just anything. Even if it generalizes from one Atari game to another, and even there we are not really there. Like Agent 57 looks a little bit like a giraffe with the wings of an eagle and the face of a lion. It's a mixture of a lot of algorithms so that it can solve more. But Nanda 7, which is Agent 57, you can Google it. It's a agent that solved more than other agents at DeepMind. It's wonderful. It's not no insult to that. Just saying that it's a collage of things. It still obviously can't learn to, let's say, survive or do homeostatic things. So I'm with you that there is something off about very sort of Roomba task specific kinds of, or very sort of limited machines. However, there is also sort of lifelong reinforcement learning, lifelong AI. There's approaches that might get closer to what biological intelligence is. And I might disagree with John that most of animal intelligence is not learned. I do think animals can learn a lot and they can do flexible things. If anything, all of like Tolman's work is based on, can animals flexibly find a shortcut, or can they sort of find a detour, etc. So I would say that animals do learn. They do have flexible behavior. However, the difference is humans can have it for way more different numbers of domain and with way fewer numbers of sort of shots for learning. Not in all domains. It's not a linear thing. I know that spiders are better at things that I'll never be as good in my life. Bats would be good at things that I will never be good at it in my life. But so it's not a linear scale. Like there are some domains in which human intelligence is not at the level of something else, but I wonder whether it's about the sensory or motor capacities as opposed to the algorithm. Regardless, I don't have an answer to that. But I want to just say, I think I might disagree with John in that animals are intelligent in a different way. And I agree with you that humans might not even be. And I also agree that machines could be improved if they are a little bit more biologically inspired. Sorry, this was longer than I thought.
Adam, so I would complement, I think, what John and I are saying. And, so one of my favorite theorems ever I've mentioned before is the arbitrary slow convergence theorem. So you tell me your learning algorithm. It can be however complicated you want. It doesn't matter. And then I'll give you a sample, and you tell me the sample size you want. Okay, and I will give you a distribution for which until you get to more than that sample size, you'll still be performing at chance levels. But in other words, this notion of a general learning is a very vague and impossible to achieve, because once I know your learning algorithm, I can always construct an adversarial example. So, this whole notion of general, there's in addition to it being fundamentally impossible to have an arbitrarily general algorithm, as you make it more general, you increase the variance. So now it takes you longer to learn stuff. And there's a real trade-off evolutionarily. As you get more general, you can learn more stuff. That means it takes you more experience to learn it. And in the meantime, you might get eaten. So I don't think we're particularly general. I think we're particularly specific. And we've learned how to do all the stuff we need to survive. And it turns out that that's why we're really good at like fine motor control. And that's why we're mostly really bad at, say, causal reasoning and calculus. Those things weren't so important for evolution, and we suck at them. And computers are much better at logic, matrix multiplication, calculus, or at least than me, maybe not than you. But so I just think we're highly specialized intellects, and the computers that we have now are specialized for a slightly different kind of thing, and that's okay.
It seems that all these responses essentially emphasize human exceptionalism. So if you think about it, of course, I mean, I think that's agreed upon, right? That as we kind of move up in evolution, one of the things that again, I hate up, okay, I mean, towards us, one of the things that we've innovated is the fact that an individual can sort of evolve new ideas in a way that required generations before, right? So humans clearly have that. But unless you're going to argue that animals don't learn anything, then you have to admit that animals have something that they're also capable of doing. The challenge is to not take it from a human perspective. How do you evaluate intelligence that's not human-centric? So if you keep focusing on language, we're out of the game. Even chimpanzees are out of the game. But compositionality, animals must understand it. It's clear that rats are able to interact with the world in a really flexible way and understand what objects are and what they do.
I mean, Adam, I think there's a real we could do a real service in this salon if we could just, it's not about human exceptionalism. If I studied sonar in dolphins, right, and I didn't study in humans, would you go, I'm sonar exceptionalist because humans don't have sonar? In other words, there are many things that I can't weave a web. I can't build a dam on a lake. I can't do 1,000 things that animals can do. Okay, so in other words, this exceptionalism thing, it just turns out that there's a kind of intelligence, whether it, like Jay said, it's instruction, whether it's language, whether it's concepts, that allow us to take shortcuts over procedural approaches to things. Okay, the final product can be intelligent. Evolution can get us there. We can build it. We can do it. There are many ways to converge on what we would all say is an intelligent behavior. Okay, so no one's denying that. Sonar is intelligent. Echolocation is intelligent. So no one's denying that all those behaviors are interesting to study. But if you say intelligence is this ability, like not many animals have, humans, to inhabit every single location on the planet, right, and do all sorts of varied things. Cats in Istanbul and cats in New York do very similar things. We have orchestras and dance and novels and different cultures and different sports. We do millions of different weird things like these salons. Okay, so that's all I'm saying is no one's being exceptionalist. No more than somebody who studies sonar on a dolphin is an exceptionalist. Okay, you have to stop saying that. Right? It's because I don't think it's a straw man. Right? It depends what you want to study. Okay, that's all it is. Okay, and if you think that there's some intelligent behavior in a mouse or a rat that you like, study it. Right? If you're going to make the claim that they can do out of sample, flexible, intelligent behavior where you're suddenly, oh my God, is that a rat using a glider all of a sudden? You know, how did it do that? Or it's using a tube as a, you know, to breathe underwater. Okay, then it starts to get weird. That's flexibility. So no one, I just don't think anyone is human-centric. We're just grappling with this ability to be so flexible. And when did it start?
So Adam, if I may add, so I added a link there. So first of all, humans are more flexible. However, to the point of learning, chimpanzees have different cultures of hunting completely depending on which environment they're in. And in Max Planck, there's a lot of beautiful work on it, field work on it, and they completely adapt to the new environment. So they hunt when in a sparse environment, they hunt individually. In a more dense environment, they hunt collectively. It's a completely different sort of social structure. Other animals, I don't know if they show as much of a flexible social structure as chimps show in this kinds of different hunting behavior. It's actually comparable to culture. I pasted a link there. I just wanted to add that to the point of, because you were mentioning chimpanzees as if they learn, not the fact that they don't learn language or they don't act like humans when they live with us doesn't mean that they are not extremely flexible and show diverse, even sort of, you know, social behavior. And we know that bonobos that are like the sort of our equidistant evolutionary cousins, they are very socially different than chimps. Chimps are violent, male-dominated. The bonobos are not, and they are female-dominated. And they actually, when you put them in each other's sort of colonies, chimps don't adapt to becoming bonobos. They don't become nicer. They don't become kinder. But and bonobos, when you take them to the chimp colony, they survive, but they don't become violent. So it's interesting. It's not just cultural in that case. That's why Frans de Waal, for instance, calls humans the bipolar ape, because we can be both. Just wanted to mention that.
But they're not as flexible, right, Ida?
They're not as. I started with. I led with that they're not as flexible, but they can have cultures within them. So they're more limited than we are. We are very good at being, honestly, anything. Like our nature is that we can rewrite the nature with civilization and culture. But it seems like we don't, and maybe there would be a smarter species than us and would be like, look at these idiot humans. They can't even change this aspect of their nature. They're so fixed. So for currently, the way that we're looking at it, it seems like our cultures are more diverse than, let's say, chimps and bonobos, but who knows?
I think that's
before you respond to that,
I think it's if you're going to bridge the gap between machine intelligence and humans, the question is, how are animals useful? And if we focus on the facets of intelligence or learning, the facets of learning that appear very unique to us, or we are particularly good at, then of course we're not going to learn from animals. So the question is, are there any examples, John, that you find fascinating enough that we could actually learn from animals?
I have a potentially example, John. I'm curious if you think it is one. Actually, I just want to point out to everyone who's here that Adam was like one of the most important people in convincing the world that rats can do interesting behaviors. So Adam is not saying that animals can't learn. Adam's career is about animals learning, but he's still making an interesting point. So with respect to learning, what do you guys think about the dog that one can train to help people cross the street? That's a thing that hundreds of billions of dollars have been invested into self-driving cars, and it's not clear that we have machines that could help people safely cross the street as well as dogs. Smart dogs can do it. So is that an example of a thing that animals can learn through something like reinforcement learning without necessarily having compositionality, without necessarily having language?
I disagree that they don't have compositionality, but I agree that they don't have language. I don't think those. Yeah.
Sorry, I didn't want to interrupt. But
the way that guide dogs are trained, and dogs in the movies, is through shaping, right? It's a form of titrated operant conditioning. All right. Now the net performance is intelligent. Right? It is. It's just that the way they've gotten there is not the same as saying to a kid, look left, look right, red means stop and green means go. Right? They just get there in a different way. And it's what I keep saying. Are you interested in the final behavior, or are you interested in how you got there? Right? And I'm just saying that they're not the same route. And you can you can then break the system by showing that you can have a poor blind person run over because their dog was fooled by some alternative traffic sign arrangement, like going to England, right? That might not happen to a human. So in other words, it's just about whether you believe in qualitative differences or quantitative differences.
John, just to let you know, Melanie and I are both saying in the chat that we think dogs have compositionality, just so you know.
Yeah, and I'm saying that I don't have an opinion on that. I don't know anything, but I can imagine dogs learning without compositionality. And a lot of the other tasks we've talked about require language, and I can't even imagine doing it without language.
I mean, we know from Standerhand's work that we can apply compositional rules to the realm of geometry without using the parts of the brain that we use for natural language. So we know that we can do language-like things for in different parts of our brains too, without using the natural language in humans, at least. So I think that, maybe we can widen our imaginations. Compositionality doesn't require language necessarily. And you learn a lot of things just by looking at it. Just, it's not necessarily, I'm confused that you guys, I'm a little confused that you guys think compositionality is language bound. It's the other way around. It's not okay, you're done thinking. Okay, good. Then I misunderstood. Zeno, we haven't heard from you. Do you want to?
Well, I came mostly just to ask Paul what continuous compositionality was. He's gone now, so. But I guess I do have a question. So when you say that you think dogs have compositionality, like, what do you mean by that? To me, I'm not exactly sure what you mean.
I think I mean the same thing that what we would mean if we wanted to test compositionality in a task. So there are certain behaviors, first of all, that we can identify that this behavior seems to imply something like compositionality. Then someone like John might come and say, hey, okay, this task looks like, from our interpretation, it has compositionality, but what about the neural structure? then my bet would be that if you go and look inside a dog's brain, you will find the sort of compositional structure. Now, to go back to your first thing, what do I mean? Let's say that I learn a representation of what a pen is, and I learn a representation of, I don't know, what sort of a piece of paper is, and somebody says, hey, can you build a sign for me? I can figure out sort of how to combine these elements that I have in a way that I can sort of stitch them together and then create a sign and hold it up.
Ida, he was asking in a dog.
I'm getting there. If you're very impatient, John. I'm not even being Nevada, okay? I'm
I've been waiting 2 hours to speak.
a bit awake, like the only distraction I have. Now, in a dog, let's say that, okay, so I'm going to mention this cat that we had. So the cat had figured out that if she opens the door with her sort of snout, then the door of the cabinet makes a very loud sound. And then she had learned that if she does that early enough in the morning, I'm going to wake up, but other people in the flat who actually were usually responsible for her food, they didn't wake up. So she would do that. So I would wake up in the morning and I would feed her. And then she would use this another time when we had left the faucet on and it was pouring into her little like thing that she was sitting on. She started doing this thing and it wasn't morning and she had eaten already. And so I come out of my room and I noticed that, you know, she's making that sound. And then I realized that she had figured out that there is like a way that she can use something else that she had used before in order to achieve a new goal that she had, which was, you know, turn the faucet off. I'm getting my blanket is getting wet. So that was something that I didn't expect her to do. Another thing was that she didn't come to sort of, this was a very indirect way to get to me. You know, it wasn't, she's opening a door, which is a combination of different things. She has to go to the cabinet, open the door, do this multiple times. It seems like, and it's indirectly going to lead to me joining, right? And she had dissociated that from the fact that this is a food signal. Like it wasn't that she just had, in a kind of associative way, associated that with food. She was capable of using this as a part of another strategy to solve a different problem. That was my cat example. I haven't lived with a dog before, so I can't. I hope I one day will. I really like dogs.
But it seems like there's at least two different things there. So one is, you know, compositionality, the ability to compose different parts. In this example, it's compose different parts of some plan versus a kind of a general means of inference, right? So you can take some behavior in one context and, you know, apply that to some other context. And it seems like, you know, your examples have combined or even composed those two things together. But they seem quite different.
You just said compose. I just want to.
Yeah, I know. That was on purpose.
If I may say that.
You know, I don't know.
Go on.
Mm-hmm. So yeah, I guess I just think that if you're gonna, like, I think maybe some of these arguments become cleaner if we know, like, if we're agreeing on the terms, because I feel like compositionality is such a broad term that it's hard to even know if we're agreeing or disagreeing. You know?
I disagree with you. I don't think it's as vague as you think it is. If this was philosophy, I would agree with you. But there are experiments. There is, like, you know, neural network models. There are tasks on this. Typically, the way would be that you would combine a number of different things in different scenarios in order to bring about a solution. So any kind of tool use in a way that some tool use that the animal has been using for other purpose and they repurpose it for something else, that kinds of things is compositionality, because you're putting things next to each other that you arrange them in a different way and you bring them in this other way. For instance, you learn that if I push my snout, I can open this. Let's call that A. You learn that if I do multiple times, this makes a loud noise. This is like the composition B. You learn that if I do this kind of or component B, the abstraction B, you learn that when you do this, Ida is going to come out of her room. And this is a sort of a C. This is a couple of things. And then D, you're going to get food. So you have learned that A, B, C, D is going to get you food. Another time, your goal is to fix sort of the faucet, right? You're not going to do A, B, C, D. If you were learning these kinds of model freeways, you would have to sort of combine them. But it seems like you have those components, so you have figured out that, you know, you don't need to run the whole program for the purpose of food. It's not that you've learned that this is the sequence I do to get food. You figured out that this is the sequence to get somebody out. And that's C in that sequence. It's not D, and it's not the reward. I'm not rewarding to the cat. It's the food that's rewarding, right? So that's in that example. In the case of models, you want them to be able to learn a representation and then use that representation somewhere else. Andrew put the definition from sort of the philosophy definition. I think that's a different case, Andrew. I think I would like to focus on the neuroscience / neural network sort of definition of it. And the compositionality in that sense has been a challenge for some neural networks. And there are some, by the way, hi, Andrew, your paper was awesome. I just want to mention that too. So in that sense, sort of, there are some neural networks that have been made. And in these cases, what happens is that they need to learn some weighing in a way that can generalize in order for them to have components that later another higher level can combine them with each other. There was a paper last year called Scattering Compositionality Learner. That was, I think, from Mila. There were other papers by Joshua Bengio's lab. There were other papers from various places. So the symbolic AI, old school AI folks would say, oh, we can't get compositionality, we have to build it in. But the learning sort of traditions would say, no, we can have it sort of come out of there based on the learning, depending on the architecture of your network. In language, it has a certain meaning. It has like certain tests, and you can see whether something passes those tests or not. In tasks, I think I agree with Adam, and your request for sort of clarification brings me there. Perhaps we can design tasks inspired by these kinds of examples once we clarify them a little better, perhaps with the help of philosophy, like the thing that Andrew was mentioned. Andrew, we have to have you up here, I guess, to talk about that. But I think we can design tasks, simple tasks, to see whether animals would do it. What I can say is that I think crows can do it, because there were these experiments where there was like a food that was on the bottom of something, and the crow would come and like fill that thing with water until it comes up and it can take that thing out. So it seems like the crow was creating a solution. It was a composition of different elements of behavior. I think in crows, I would bet it like that we would find it much easier, maybe. They're very good at sequential stuff. I don't know about rats, honestly. It seems like anything they do takes like forever to learn, like 6 months. Same with monkeys, actually. Like they take a very long time to learn simple tasks, from what I've heard, and I haven't done experiments myself. I've just seen my friends suffer at different sort of training their animals. But I think that we can design some tasks. Sorry, I just droned. I talked a lot. I'm going to quiet my microphone now.
I mean, I just want to say that I think that if you look at the animal learning literature on compositionality, and whether you use the Stanford Encyclopedia or others, it is very complex. And I'm afraid the cat example doesn't convince me at all. I think there are alternative explanations. It's hard, just so you know, when you try and prove the kind of syntactical combinatorials that humans can do, which is where these definitions in the Stanford Encyclopedia come from, because they are language centric. You're right, Adam. It is hard to prove that. And by the way, when it has been done in the animal kingdom, it's usually done looking at things like vocalization in marmosets, where they're trying to see whether you can get from there. So in other words, it's an interesting issue. There's no room for dogmatism, but it is hard to show it. And even if you do show it, to me, it's a form-frust version of the remarkable explosion that you see when it comes to human primates. So in the end, we're going to have to explain the non-linear transition, even if you find form-frust versions in vocalizations in marmosets and other primates, or in crows or wherever.
So I just invited Andrew on. Hey, Andrew. I just said you had things to say that would be relevant, so I wanted to hear them.
Yeah, I'd like to hear what I have to say that's relevant too, actually. No, I think that.
Oh, can you introduce yourself? I think people might not know you.
Oh yeah, sorry. I'm Andrew. I am a research scientist at DeepMind, and I graduated from Jay's lab recently. So, yeah, and I'm interested in issues around like language grounding and compositionality and zero-shot adaptation in deep learning. And I think that like, I guess all I would say is that I think it's very hard to come up with a definition of compositionality that captures all of the things that we mean when we say compositionality in sort of like these contexts. And I think I'm kind of just repeating what other people said before I got on.
So I know you're having Google issues, but if someone can share a link or something, I think that this issue of compositionality comes up all the time in these discussions, and I'm just confused. I think like Zena maybe, which if someone were to show me a proof, like this is a problem that's compositional. If your algorithm learns compositionally, it'll say converge faster. In any domain, it can be totally arbitrary. That would be really interesting to me. And then I would say, oh, I know what you mean. And of course it's true then. And until that, I feel like kind of what John is saying, like, I bet there's a way around it without doing compositional stuff that you can just learn it.
Okay, my Google is working, so I'm going to start posting links while others are talking because there is so much work in compositionality and artificial intelligence, Jovo. I'm just not going to be able to do it justice. I'm just going to post those links there. I think a review would be useful at this point because the notion in language is very different than the notion in artificial intelligence and the notion in tasks. I disagree with John that it's always linguistic. There's a lot of other tasks, but I'm going to be quiet so somebody else can reply.
Maybe we're saying that it's almost 7 o'clock. Maybe we're tired and should go.
Yeah, just to, about the linguistic, non-linguistic, it is tough, but compositionality, Zena, for me, and I think for you is, when in a sentence, the position of the words in that sentence and the meaning of the individual words in that sentence determine the meaning of the whole sentence, right? And it's that fundamental thing, the sentence and the meaning of the words in it together provide meaning. And when it comes again to trying to teach that kind of understanding even to non-human primates using sign language or human language, they fail rather miserably. They learn it associatively, right? And even if you've got little, and 5%, 10% of the time you can see evidence for some compositionality, it's just a very stunted version of what we seem to do almost effortlessly. Right now, whether one can come up with a non-linguistic version of combinatorial meaning and things like that, I'm just saying it's difficult, right? And the cat example, in the animal behavior kingdom, it is difficult, and the evidence is hard to show. I'm sorry, it's just hard to show. Now, whether the AI community have their own version, fine. Maybe this can be part of your project, Jovo. We need to be taught, right, by you and Ida about how these concepts feed back into behavioral.
By Ida, I don't know. Only Ida knows. Maybe also other people, but certainly not me. And it seems like Ida does not.
Wait, what happened? Andrew was going to say something because he's done some work in this field and he linked a nice a link to the philosophy definitions. Andrew, do you want to go ahead and say a little bit because you've done some work on this actually that's related?
Well, but I don't see the thing is that the work I've done on compositionality really does come down to language type definitions as well, right? So I don't know if I can attribute anything to that. What I would say, I think maybe on the opposite side, why I think the definition is so hard and why the language sort of definition doesn't work is because the nice thing about language that allows you to write down sort of formal statements like this or talk about it in terms of breaking a sentence down into its components doesn't hold as nicely for the real world because it's not really clear what the components are, right? Like in the visual scene I'm looking at right now, every leaf on the tree out the window could be a component on its own. It's not like my representation of the world can be compositional in the sense that, like every component, like every leaf on that tree is a separate component in my representation. It needs to be more compositional in the sense that I could break it down and attend to any particular piece of that if I wanted to. And so I think that like trying to find a notion of compositionality that's static might be problematic. It should be more about the ability to decompose things on the fly. And I think to capture that kind of structure, you'll succeed more with continuous representations. But I don't think that we've fully succeeded at that yet.
So here's one thing I do want to add. So I linked a paper there. Anirudh Goyal is the first author, which is called Object Files on Schemata, Factorizing Declarative and Procedural Knowledge in Dynamical Systems. This is a collaboration he did with Yasha Benju and others. Something that they are, thank you, Claire, for documenting the links. Something that they showed is that, in fact, something that Jay mentioned as well. So they're using transformers. Transformers are what they use for BERT, for instance, for language models, but not at all for language models. In this case, you start to learn certain things using the transformers. You start to learn, for instance, things, they have the object files and they have the schemata and the multi sort of stacked transformers. So one just learns certain kind of weights about the things around the world, and one learns weights about those weights. And what you get in your schemata are things like something is to the left of, something is on top of something, etc. So in that way, they can combine the same schemata with multiple objects. We are in collaborations to sort of extend that work and to sort of get it into sort of maybe hopefully in a series of work into compositionality. But I think that is a very promising approach, because it starts off by by decomposing the sort of representations into objects and into sort of schemata that can be applied to multiple objects. And I think that is a very promising approach for using, in this case, deep learning, and in this case, sort of the transformer approach. Do I think it's the end of it? No. Do I think it's like hopefully the beginning of a lot of work that is related to this? I hope so, because this is like an area that I do care about. And right now, Ferial just added a link that I'm going to take a look at. Right. So she just added a link from DeepMind. Matt Botvinnik is a co-author on this, and Shakir Mohammed from people that are friends of the, vicinity of our colleagues. It says learning basic visual concepts with constrained variational framework. So thank you, Ferial. I'm going to take a look at that later. I do think that maybe we can get Ferial here. I don't know. Everybody's has sound issues anyway. So I don't think it's constrained to language at all. And I don't think we are too far from it with neural networks. And I do think that there is a nice way of defining better tasks, perhaps. The tasks that people do use, for instance, Raven's progressive matrices, I think, is one of the things that they use, which is not linguistic. And they use it to test compositionality in people. And there was a paper last year at ICML that actually could solve that. It was called, I think, Scattering Compositionality Learner or something like that. So there are tests that are non-linguistic, John, but you're right that they're inhuman. I'm not an animal researcher, and I don't know of a standard animal task to test compositionality, but I'm sure we can design a simplified progressive Ravens test for animals if someone hasn't done it. And I apologize if someone has done it and I didn't know. Thank you, Andrew. Yeah, Scattering Compositional Learner. I remembered it. Wow. Yeah.
So I don't have to, but I'm going to go eat dinner with my children now because I love them and miss them. So you guys are welcome to keep going. John, you're silent.
I have to go too. I'm all alone in this office building. I'm terrified. So I'm going to
come over.
It's spooky. It's too spooky. But this has really been great. I mean, we need to just discuss this more. It's actually really interesting.
Awesome.
Thank you, everyone.
Thank you, everyone, and celebrate.
I don't know how many people stayed with us.
I hope everybody celebrates the blue light. Thank you, Georgia, and thank you, Philly, and thank you, Arizona. Yeah.
And Jane.
Thank you, Jay McClelland.
Jane Wayne, Andrew, everybody else, Adam.
Thank you, everyone who was on stage, on screen. Yeah.
Carol, next time, hopefully we'll get you on.
Yeah, I hope to see everybody. Oh, yeah, Irina Hage, indeed. Thank you, everyone. Hope to see you next week. And yeah.
Enjoy.
Ciao. Thanks. Bye.
No, you hang up.
Everybody else.